Okay, let's go ahead and get started. So the plan for today is to talk a little bit about linear approximation. Again, this won't be on the midterm, on this upcoming midterm. So we'll do that for like the first a third to half of class, and then for the second part of class, we'll do a review game. So I'll split you into teams, and it'll be like a true-false review game. Okay, so let's first just talk about linear approximation. So the idea here is, let's say you have some function like sine of x, and you want to estimate the value of that function. So like, this is like what your computer is doing, right? Like if you ask your computer, like, what is sine of 0.1? It doesn't have necessarily a way of calculating that precisely, but it has a method for approximating it up to any decimal precision that you would like. So linear approximation is sort of like a first step towards that. And basically the idea is that the tangent line at a specific point, so let me draw a graph of a function. So let's say we're looking at sine of x. So if I take this, if I want to know what the value is close to, say, x equals 0, and I draw the tangent line, which we know how to calculate because we've been doing derivatives, that line is actually a pretty close approximation to the function if I plug in just values that are close to 0. So the idea is that close to, in this drawing it's 0, but like let's say close to x equals a, the tangent line to the graph at the point a comma f of a is a good approximation of the function. So sometimes like it's easy for whatever reason to calculate what the function is at a specific value. So for example, like for sine of x, we know that sine of 0 is 0. And there, we know several other values of sine just for theoretical reasons. But then for values close to that, we need some way of approximating what those values would be. And the other thing is that it's very easy to evaluate a linear function at whatever point you want, right? It's just multiplying whatever the slope is and maybe adding a number or something. So it's like going to be a lot easier to calculate than some other things like sine of x. Okay, so for this, we'll make a definition. And then I'll do a few examples. So the equation of the tangent line at A is the following. So this is nothing new. We know that this is given by y is equal to f of A plus f prime of A times x minus A. Maybe I'll just pause and explain why we know that. So if you think about it, this is just a rearrangement of the point slope form. So this would be like y minus f of A is equal to f prime of A times x minus A. Right, so we know that the tangent line passes through the point A comma f of A, and that the slope at that point is given by f prime of A. Okay, so does this make sense why we have that equation for the tangent line? Okay, so then I'm gonna make a function out of this. So I'm gonna let L of x be equal to that same thing, f of a plus f prime of a times x minus a. So this is just the function who has this as its graph. And this is called the linearization of f at a. Yeah, it's just, yeah, it's okay, so this is the linearization of f at a. And so the idea of this method is that for x close to a, we have that f of x is approximately equal to this L of x. Okay, so that's sort of like how this linearization is used. Are there questions at this point? We'll do a couple of examples. Okay, so let's do the following example. And I love this because, so what we're gonna do is we're gonna estimate the square root of 10. And this is actually sort of amazing because it's almost like a party trick. Like you could just do this on a napkin or something, but it actually approximates the square root of 10 up to like 2 decimal places accurately, which is kind of cool. You can just do this by hand. So what do we need? We need a value that's close to 10 where we know what the square root is. So what should we take for a? Yeah, 9, because we know what the square root of 9 is. So we'll take a to be 9, since we know that the square root of 9 is equal to 3. Okay, so then I'm gonna let f of x be equal to the square root of x, and then I know that f of x is approximated by this linearization of x at the point 3. And so what is L of x? We'll just write this out. So this is f of a plus f prime of a times x minus a, and a is 3 everywhere. Let me just plug that in. Okay, so we need to know f prime of 3. So let's just do that on the side. So let's calculate f prime of x and then plug in 3. What is f prime of x in this case? So f of x is square root of x. Yeah. Yes, a is, sorry, a is 9. Sorry. Yeah, so we're plugging in a everywhere, so it should be 9. Thanks. What is f prime of x? Yeah.
1/2 radical x.
Yes, yeah, so f prime of x, this is 1/2 root x. How did you get that?
So that's x to the 1/2 minus 1 from the 1/2, and that would be x to the -1/2 times 1/2, and then.
Yeah, so, okay, so this is, you can think of this, as x to the 1/2, and then use the power rule. So you would get, so using the power rule, you would get 1/2 x to the -1/2, which is why you end up with this in the denominator. Does that make sense? Yeah.
On a midterm, should we say like using power rule, we got this, or can we just write the if we show it?
It's better if you justify your steps, because then if you make an error somewhere, it's easier for me to say like, oh, you did this part, like this is why you did this, or something like that. So it's easier for me to give partial credit if I have like some indication of what you're thinking is. Other questions? Okay, so then we plug in 9. So this is going to be 1/2 root 9, which is 1/6. Okay, so then I'm going to simplify, go back over to the left and simplify everything. So f of 9 is 3, and we're adding f prime of 9, which is 1/6, times x minus 9. Okay, so that's our linearization at a equals 9. Are there questions so far? Okay, so now I'll just plug in x equals 10, because that's the value we wanted to know. So we get that the square root of 10 is approximately 3 plus 1/6 times 10 minus 9, which is 3 plus 1/6. And if you write out the decimal expansion for this, this is 3.16 repeating. And the actual value of root 10 is 3.16227, some other stuff. So this is pretty cool, right? Like, it's a very simple idea. It's like, we're just gonna pretend the function is linear and use the slope at that one point. And it actually gives you a decent estimate of the value of the function. And of course, it's going to get worse. Like if you go further and further away from 9, your approximation will get worse and worse. But if you take values close by, it'll be pretty good. Yeah, do you have a question?
Yeah. You're saying you can do it to any number of decimal places that you want? What would that process be?
Yeah, so you could imagine like taking in, like factoring in like the second derivative, for example, like that'll tell you how fast is the slope changing, right? And so that will help you get a closer and closer approximation. And similar reasoning, like you can take into account the third derivative, the fourth derivative, and so on. So this is something that you'll do in 1301. That's something called a Taylor series, which is basically gives you a way of approximating your function using a polynomial. So this is like the degree 1 version of that. But yeah, there's a way you can take as many as high a degree polynomial as you want, and you'll get a better and better approximation. It's like factoring in higher derivatives. But yeah, that's coming. If you continue on in 1301, that's next semester. Are there other questions for us? Yeah.
Like again, after you do like the f of 9 and 100, why is the first term 3?
Because f of 9 is 3. Because f is square root. Yeah. Are there other questions? Okay, so I'll do one other example. So we'll go back to the sine example. And this approximation is used a lot in physics. So physics uses the following approximation, which is, we'll say sine theta is approximately theta near zero. So this is like called small angle approximation. So if you put in an angle that's close to zero, then a lot of times physicists in like a complicated calculation will just replace sine theta with theta everywhere. Is this something? Is anyone in here in a physics class who's seen this happen? Yeah. So we'll justify that now using this linear approximation. So why can we do this? So we'll have that sine of theta is approximated by this linear approximation, which is going to be given by sine of 0 plus the derivative, so d dx of sine x evaluated at x equals 0. That's what this notation means, is like take whatever you get from this calculation here and evaluate that at x equals 0. And then we'll multiply that by theta minus 0. Okay, does it make sense how I got this line? This is just like plugging in everything from our problem, so our choice of f, which is sine, and then our choice of a, which is 0, into the equation for L of x, or in this case L of theta, which everything. I'll put theta here. Okay, what's the derivative of sine? Cosine. So, and what is sine of 0? So we get 0 plus cosine of 0 times theta minus 0. What's cosine of 0? Yeah, so we're just left with theta. So that's our small angle approximation. Are there questions about the? So like, how good of an estimate is this? I just plugged in. So this would tell me that sine of like 1/10 is approximately 1/10, which is 0.1. And the actual sine of 1/10 is equal to 0.0998, and then some more decimals. So again, it's pretty good. It disagrees with this decimal, but if you were to like, truncate this and round it, you would get 0.1. So pretty good. Are there questions? The other thing you might wonder is like, how close do the values need to be to A? And there is a way to bound the error. And that's again something that you'll see in 1301, is that you can say like, you actually can guarantee like up to some number of decimal places this is accurate.